So here's where Phoenix went. Phoenix went to 68 degrees north, and here I've shown the other missions that has landed successfully. You can see they're much closer to the equator, particularly Spirit and Opportunity. Phoenix is just about as far north as you could go. You see, if it went any further, it'd fall off the planet. Space right there. So that's why we knew that it wouldn't last the winter. And here it is when we land and look out, we see just what we'd expected to see. We see a polar environment. We see patterned ground. The characteristic polygonal ground you see in ice-cemented terrain, like you see in the north here, north in the Arctic archipelago in Canada. And then looking underneath the spacecraft, we saw the ice. There it is, right. The rockets had blown away the dirt and revealed the ice-cemented ground. And this patch of ground was named Holy Cow. The words that first came out of people when they saw it wasn't holy cow, but it got toned down. So we found ice. Now when we saw that ice, it was a big thing in the media. Phoenix discovers water on Mars, ice, da 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 da. But in fact, that was not a surprise. We knew that there was going to be ice there, or we very much expected it. The reason we landed where we did was because we had data that indicated that there was ice at these locations. This is a map of Mars showing the distribution of water ice based on the Odyssey neutron mode of the gamma ray spectrometer. Water, H molecules, thermalize neutrons. And they're the only atom that really does that. And so a map of thermal neutrons is effectively a map of H. And on Mars, H is water, H2O. And that's how the Odyssey gamma ray instrument mapped out the neutrons, mapped out the water on Mars. And you see these blue regions in the north and south indicating mass fractions of ice of about 50%. So we expected ice, and we chose the landing site to be right in this big blue spot so that we would land on ice. Scientifically, the big news would have been if we hadn't found ice. That would have been quite a surprise, a disappointing surprise. But finding ice was not a surprise. Now this site is very interesting to me in terms of life because it's probably the spot, or the region, which on Mars could have been habitable the most recently in Mars history. So the most recent habitable place on Mars is the Phoenix site. And the reason is that the ice at the Phoenix site could have been liquid 5 million years ago. What was happening 5 million years ago is the pole, the axis of Mars was tilted 45 degrees compared to 25 degrees today. So today, Mars is tilted 25 degrees. Very similar to the tilt of Earth, which is 23.5 degrees. As a result, seasons on Mars are very similar to seasons on Earth, except the sun is, solar flux is 1/2, because Mars is 1.58 feet away. Question here?
How did you figure out that it was 45 degrees 5 million years ago?
By doing a calculation of, think of Mars as being a top, and it's just a spinning top. If it was the only thing in the universe, it would never change. Its angular momentum would be fixed in this direction. But it's not. It's being torqued by Jupiter in particular. And Mars is oblate, so it's like got handles on it, if you will, and Jupiter is torquing that, trying to put those handles in the plane of the solar system, and Mars is tilted, and that torque causes Mars to precess and mutate. And you can write down Euler's equations for motion of spherical tops and work it out, and work them backwards from the current state of the solar system and calculate what Mars would be doing. Earth experiences similar obliquity changes, but much smaller in amplitude because Earth has a big moon that acts effectively as a gravitational outrigger, stabilizing the Earth. But Mars doesn't, and so you can work backwards these calculations, and you can see 5 million years ago, the obliquity was 45. Calculations only go back about 10 million years, and then the solutions become chaotic, mathematically speaking. So you can get statistical behavior of the solutions further back, but you can't get a detailed solution. This was first realized by Bruce Murray in a seminal paper, the most recent calculation done by Lascar now. As computers get better and better and better, they're able to do this with more and more precision. Question back?
Sir, if Jupiter is trying to make Mars flat, then
Yeah.
wouldn't it be more than 45 degrees nowadays?
It goes more and less. You see it's going up and down, up and down. It's a top. Think of a top mutating and precessing. I can't give you a detailed explanation for why it's 25 now and why it was 45 then, but it just moves all over the place.
Also, maybe one point it was like 35 and then it goes back to 45.
Yeah, you can
and
see it.
goes
It's 25
up.
now, it was 35 then, and then down, goes up and down. This is a plot of the value of the obliquity versus time. And so here it is today at 25. If you were around, say, 500,000 years ago, you could have seen it go from 35 down to 20, and so on. It's oscillating up and down, up and down. And what's interesting to me is that when the obliquity is high, the summer sun is quite high in the sky. So imagine you were standing at the Phoenix site or the pole on Mars. Today, the sun would get 25 degrees high. 5 million years ago, it would get 45 degrees high. Well, cosine of 45 divided by cosine of 25 is about 2, which just about compensates for Mars's increased distance from the sun. Which means that 5 million years ago, there was twice as much sunlight hitting the Phoenix site in summer than there is today. There was as much sunlight hitting the Phoenix site in summer as is hitting the Earth polar regions today in summer. So the poles on Mars were as sunny as the poles on Earth today. So if you went up to Resolute, which is about 70 degrees north, you would have the same sunlight in summer as the Phoenix site 5 million years ago. And Resolute, as you all know, gets muddy in the summer. So that's why we think the Phoenix site could have been muddy 5 million years ago.
But there's no atmosphere, so there's no greenhouse factors.
The pressure at the site is high enough, unlike the South Pole, the North Polar region, the pressure at these sites is high enough that liquid water is stable. Right? As you remember, Mars has a crustal dichotomy. It's a very good question. It's important to understand the difference between the South and the North. I don't have a topographic map on Mars, but if I did, you'd see that the northern plains are at a mean elevation of about -2 kilometers. And the southern plains have a mean elevation of +2 kilometers. As a result, the pressure in the northern plains is always above the triple point of water. The pressure in the southern plains is always below, which means that warming up ice in the southern hemisphere doesn't generate water, it just generates vapor, whereas warming up ice in the northern hemisphere will generate water. And you can go back and look at the Viking pressure sites. Viking, we have the best data record for pressure at the 2 Viking sites. Viking was at 40 north. This, in fact, is a topography map of Mars. Yeah. And you can see that this whole region is quite low. Viking, if you look at the pressure reading, it was never below about 8 millibars. So water is possible in the North Pole, but not in the South, where the elevation is quite high. So that's why the Phoenix site is interesting from an astrobiology point of view. So here I'm going to now start talking about what we found at the site. The first thing we found, or didn't find, or what I think was conspicuous by its absence, was rocks. Look at that site. There's no rocks there. You could play a game of baseball on this ground. It's flat, no rocks. Compare that to the Viking 2 site. Here's the Viking 2 site. You couldn't play baseball on that. Look at all those rocks. Until Phoenix landed, we were using this as our design model for polar missions, because it was the furthest north we got. So we were designing for big rocks. Where are all the rocks? I don't know. Nobody seems to care. I asked the geologists and they sort of brush it aside. I think it's an important question. Where are all the rocks? What happened to them? Is there something, what breaks up rocks on Mars? On Earth, what breaks up big rocks into little rocks is water and salt, as you know from potholes in the winter. But on Mars, there's not much water and there's not much salt activity. Well, maybe there's salt. So it's not clear. And this just quantifies that. The Phoenix site has less big rocks than any of the other sites we've been at. That's a mystery.